All right, welcome back to another exciting episode of CS250B. Today we'll take a little bit of time, probably just this one lecture, talking about cache-efficient algorithms. And we talked about, in the past couple of lectures, we talked about cache architectures and at a low level, how to write software that takes advantage of it. And today we're going to talk a little bit about how that sometimes becomes complex or difficult, not very portable to do. And we're going to take a little bit of time looking at a class of algorithms that actually kind of automatically does a good job of being cache efficient. Hopefully today, and absolutely this deck of slides will be the, at least for now, the last part in talking about cache systems. After that, we'll go on into, after this, we would have, starting from a baseline software implementation, a hypothetical baseline software implementation. After this deck of slides, we would have moved the performance bottleneck away from the memory system, where it often is, to, well, away from it, basically. And when we do that, they typically move on to actual raw computation throughput. So starting from the next lecture, we'll talk about how to improve that. And who knows, maybe the performance bottleneck will move back into memory systems. And at that point, we'll be making good and effective use of our system. Okay, so today's topic is cache-efficient algorithms. So if we go back to the matrix multiplication example for a second, we talked about doing blocked matrix-matrix multiplication. When we take a matrix A, multiply it against matrix B, and then we want to create, matrix C out of it, we will divide the matrix A and B into a grid of submatrices, and then we will multiply a bunch of these submatrices together and then sum them up. That gives us, if we do a recap, a one full read of the B matrix does result in a number of the S number of rows in C, also S number of reading S number of rows in A, meaning because we need to scan over A total of N divided by S times, the total number of times you have to scan through B also becomes N divided by S times, which is much, much better than having to do it N times. And that was the recap. And the best performance we can get from this blocked matrix-matrix multiplication comes when the size of S pretty much matches the size of the cache that we have on the system. So because S is either the width or the height of the sub-block, when N squared is kind of the size of the cache, we would get the best performance. If we, and S is a machine-dependent magic number, pretty much. For subblocks of size S by S, we need to do N multiplied by N divided by S reads for matrix B from memory. The question is, what S do we use? We can either optimize S. One thing we could do is try to optimize S for the L1 cache. That would be optimizing for the L1 cache would be the most straightforward thing to do, because we have seen that only when something does hit L1 cache that we don't get any performance degradation. Any other cache, we still do get a little bit of performance degradation. So this would, optimizing for L1 cache could be at least a reasonable first step to do. The question here could be, the L1 cache for me is 32 kilobytes because I'm using a certain Intel processor or whatever. Who knows for what else? L1 data cache could be, different sizes for different processors, different even compatible processors from different manufacturers, etc. And if S by S, X multiplied by S, exceeds the cache, we would lose performance. In fact, we will see a pretty sharp decline of performance, because at that point, we'll be back to thrashing the cache again. On the other hand, if S by S is too small, you also lose performance, because we wouldn't be making the best use of the available caching resources. We could be reading, we could have been getting by with reading B a much fewer number of times, but because we chose a small s, we could be doing more work on the memory system than we had to. Of course, compared to the situation in which the submatrix exceeds the cache size, where the performance has a pretty sharp decline, choosing an S that is smaller is, I guess if you have to choose the lesser evil, that would be it, because there we would see a kind of a more gradual performance decline, but a performance decline nonetheless. Another dimension of issues is that, do we ignore the rest of the cache hierarchy? Because if we optimize S for L1 cache, we pretty much ignore the rest of the, we'd be thrashing L2, L3, and whatever else cache that we have in the system. On the other hand, if say we optimize S for L3, if S by S is the size of the L3 cache, then maybe we can have another dimension of submatrices, where if we divide the S by S matrix, submatrix, further divided into T by T blocks, optimized for the L2 cache. That would be a way to get performance. And maybe because we also have the L1 cache, maybe the T by T multiplication can be further divided into something like U by U blocks for the L1 cache. And here we have pretty much added the two more magic numbers into this methodology. And if you're running on a system that has an L4 cache, that adds another magic number. If you had optimized these numbers for a machine with a particular cache hierarchy that has an L4 cache, and we try to run it on a system that only has 2 levels of caches and are much smaller, then we go back to thrashing the system already. So this kind of an approach is something that you can absolutely do, and in fact is done many times, especially for very sensitive performance sensitive things like scientific computing applications. Because if you're running things on HPC clusters or supercomputers, then we know exactly which machines we're going to be running on, and wringing the last bit of performance from these systems become more important than trying to make the software be portable to smartphones or whatever. But if the software we're writing is not intended for that kind of a specific situation, if we want to write something like, I don't know, BLAS, where we want the software library to be used across a reasonable range of desktop to server class machines, and this becomes a problem that we have to solve. And in this lecture, we're going to just do a very high level, very taste of algorithms called a class of algorithms called the cache oblivious algorithms. Cache oblivious algorithms comes in many shapes and forms. So we're going to take a high level look at a couple of them, just as a tool to have in the back of your heads. These class of algorithms, the goal is to require no explicit knowledge of cache architecture and or structure. The only requirement, often even this is not true, the only requirement is that a cache does exist. The system does have a cache, and it consists of a hierarchy of memory, faster memory as they get smaller. And this is pretty much, you can pretty much expect this to be true in most reasonable machines. And also, this is kind of not very important for our high-level purposes right now. This point becomes important when you try to actually do algorithmic analysis on these things. But I guess I do need to point this out before we move forward, which most cache oblivious algorithms, and especially the ones we're going to look at, depends on this thing called the tall cache assumption, which is natural. We don't have to worry too much about it. The tall cache assumption being, if you have a cache of size B bits or B bytes, M bytes, and each cache line is B, meaning we have M divided by B number of cache lines. B squared, which is the size of the cache line squared, is still smaller than total number of bits in the cache M, multiplied by a small c, which is smaller than something like 1, for example. And this is pretty much always held in modern normal machines they would come across, because say in a modern L1 Intel processor, the total size of the well, I guess I used 64 kilobytes because I guess I was counting iCache and Dcache at the same time. But yeah, 64 kilobytes being M, 16 bytes being B. 16 squared is still much, much smaller than 64 kilobytes, meaning the tall cache assumption does hold. And this is not particularly important. You don't have to memorize this equation right now, at least for the purposes of this particular lecture. But I guess I had to have it here for the sake of completeness. The goal of cache oblivious algorithms is that they still need to be mostly cache optimal. I mean, as much as they can be. And most of the cache oblivious algorithms that we will look at is typically a recursive divide and conquer approach to solving problems. Recursive being, hopefully, as we recurse to smaller and smaller units, we will reach a point where automatically, at a certain recursion point, we will be optimized for L3 cache. Further down the recursion, at some point, we'll be optimized for the L2 cache, so on and so on. Right. I think I had a line here. Yeah. Yeah. If this is not, again, this is not important. This is just here for the sake of completeness. The reason tall cache assumptions are important is that if we have a shorter cache, meaning not tall, short, where B squared is larger than Cm for a small c, if you have a shorter cache with very, very long cache lines, if we think of an extreme scenario, we can think of caches with, say, 64 kilobytes cache, but each cache line is 2 kilobytes, for example, which is not something that people typically do. But if we have something like that, they cannot efficiently, at a high level at least, they cannot efficiently divide data into small blocks. And that's why one of the big reasons that we have this assumption. And this is a natural assumption to have, so we don't have to think too hard about whether the systems that we target have these characteristics or things like that. And as kind of a peek into the future of this course, topics like cache oblivious algorithms also do become more important as we add things like the storage and network into the system. Because caches, as we have talked about, is a way of handling things like bandwidth and latency. And because latency, let's say latency of off-chip DRAM is significantly slower than on-chip memory, and that's why we needed it. And latency becomes even larger as we go off-chip, off machines or beyond memory. We remember that the access latency of caches are in the orders of nanoseconds. If you go to the access latency of DRAM, we go to hundreds and thousands of nanoseconds. If you go to network, if you go over the network to remote memory, for example, if you have a distributed systems, if you have a disaggregated memory, if you have data structures distributed across a cluster, the required latency of access becomes multiple orders of magnitude higher. And this storage, if you go to storage, and because we need more capacity or non-volatility when power goes down or whatever, the latency becomes, I mean, this depends on the storage technology, and we'll get to it in one of the later lectures. But if we start going to storage, then the latency also becomes another multiple orders of magnitude slower. And access granularity of data access becomes also larger as we go off chip, as we go off machine. And this has multiple reasons, including trying to hide the latency of access, because if we have to suffer large latency anyways, increasing the basic unit of work that we do per latency, because we're suffering high latency anyways, we might as well do a lot of work when we do it, and also many other reasons. But access granularity also becomes much larger as you go off machine. When you're accessing cache lines, or if you're accessing DRAM, the access granularity is in the order of cache lines, where it's something like 64 bytes. But if you access storage, at least if we access storage in a, well, yeah, if you access storage, then the latency becomes in the order of pages, where each page is 4 kilobytes to 16 kilobytes in size, depending on the technology. And yeah, all these numbers come with a significant number of caveats, hopefully something that we will have time to actually go over in one of the later lectures. And here's a link. I will actually post this link to the course website as well. It's a very, very important link that I think we should all check out every couple of months to see if anything that we know has changed. Latency numbers that every programmer should know, comparing the latency of things, everything from things like caches all the way to storage access and remote system accesses. I implore all of you to actually, if you haven't actually looked at this website already, I implore all of you to go check it out after the lecture. Anyways, in terms of the class of algorithms that we'll be looking at this lecture, there's 4 prominent ones. Hopefully we'll have time to go over all of them. Matrix multiplication, because it's pretty much legally mandated to look at matrix multiplication when we do high performance stuff. Merge sort, stencil computation, we'll get into what that is in a bit if for those of you who are familiar, and trees and search. I think we're actually, yeah. And one driving example here is, I don't know, I'm pretty sure all of you have implemented quicksort in C or a similar language at some point. And I don't know if you actually tried this, but try writing quicksort, best effort quicksort in C. And then measure the performance of how long that takes, sorting something like, I don't know, 10,000 32-bit elements. And then try doing the same thing with, in C++ at least, try doing the same thing with std sort or boost sort or one of those provided libraries. If you haven't done something clever, there's probably going to be quite a bit of performance difference between something textbook quicksort implementation and something that std sort or boost sort or whatever implements. And despite the fact that the quicksort algorithm itself has a pretty much good time complexity things, it's not an issue of time complexity most of the times. And the big reason this happens, one of the big reasons that this happens is exactly the things that we're going to talk about in the next couple of slides. So hopefully, yeah, I think textbook example quicksort implementation performs something like at least 4 times worse than std sort in my experience. So that could be an interesting thing to check out. Anyways, back to matrix multiplication. In the context of matrix multiplication, our question that we need to solve using cache oblivious algorithms becomes, how do we make sure that we choose the optimal value for S being the size of the submatrices? How do we make sure that we choose the optimal S value so that it works for all cache levels? And without further ado, the solution is that we do matrix multiplication recursively. For example, if we're multiplying A and B to get C, A, B, and C can all be chopped up into 4 different pieces, submatrices, dividing it along the half line, vertically and horizontally. If we do this, the formula for calculating the matrix multiplication becomes this. We multiply A1 by B1, A11, B11 here. And then we add multiplying A12, this one here, up top right, against B21, bottom left. This is pretty much, what you expect from regular matrix multiplication. So here you see the sum, A11, B11 plus A12, B21. And the same for all 4 other slots. And yes, matrix multiplication can be expressed in this form with 8 multiply additions of half-size matrices. So in terms of the number of elements, quarter-size matrices. And we could do this, we could use this approach to chop up, let's say, the C matrix into 4, and then the resulting 4 submatrices again into 4, again into 4, and again into 4, until the submatrix size is very, very small. if we do this, I guess once the submatrix size becomes very small to the point that we know that it fits inside one cache, for example, we could do something extreme like 16 elements in the submatrix or something like that. If we do something like that, hopefully over the course of recursing down into small numbers, we will pass through optimal sizes for where the submatrices fit in L3, L2, and L1 cache. If you were to do a little bit of performance analysis to try to convince you that this actually does work, in terms of the work that we have to do, and again, I don't think this is important to try to memorize this at this point. I'm just putting it out there to try to convince you that this is indeed an effective and efficient way to do things. Right, because at every recursion level, we are chopping the matrices up into 4 parts, resulting in 8 submatrix multiplications. Remember, because each resulting submatrix in C required 2 matrix multiplications and then addition of the 2. And because we're chopping the matrix up into halves, at least in the in terms of width and height, so the recursion tree depth for an n by n matrix would be log 2 of n, and each fan out of each node of the recursion tree depth, the number of submatrix multiplications that you have to do is 8, because we need to do 2 matrix multiplications per submatrix. So the total amount of work that we have to do is 8 to the power of 2 log 2 by n, which numerically we swap the 2 and 8 becomes n cubed. So the same amount of work. Doing this does not result in us having to do more additions. It does not result in us having to do more multiplications, at least in terms of time complexity. More importantly, if you look at the amount of cache misses that we have to suffer, and again, this goes into the weeds a little bit, but you don't have to memorize this or anything. This is just to convince you that this works. So the recursive tree for cache access has a depth of log 2 of n, again, minus half of log c of m. And the minus here happens because log 2 of cm. The minus here, the subtraction here exists because we want to stop recursing when n squared, the submatrix size, is smaller than the smallest size of the smallest cache. So this happens. We're not in terms of cache misses, we're not going to recurse all the way to log 2 of n. We're going to stop somewhere where the matrix size becomes small enough to fit in the smallest cache. So the number of leaves in this recursion tree becomes power of 8 to the power of log n, subtracted by the same thing, which turns into, after normal high school math, turns into this. And because at the leaf, we load the cache size divided by b cache lines for each of these leaves, the total cache line read becomes n cubed. So if we do just normal n cubed, that would be the vanilla case with no blocking, no nothing, because we would be loading n by n matrix B, n times for A. But we're dividing that by B multiplied by square root of n, which is, besides just by eyeballing this, at least looks to be a much smaller number than n squared, but it is pretty much theoretically proven that this is an optimal amount of cache accesses. And we're not going to go into details about how that's proved, except to just show you that there are citations that say that this is indeed optimal. So yeah, this approach does give us the same amount of work. It's not adding any, at least in terms of time complexity, it's not adding any more work. And by doing this, the cache access characteristics is optimal. Also, this is sometimes a problem with recursive algorithms is that if we recurse down too many times per work, the recursion overhead sometimes does dominate. But even for pretty big matrices, if we are recursing down only log 2 of n times, the recursion function call overhead for the recursion is also not very high. And here's actually some performance numbers from this approach. This was taken from a course slides from somewhere. If we compare the performance of a naive matrix-matrix multiplication with no cache effects compared against the cache oblivious implementation, when the matrix is very, very small, and when the whole thing fits inside cache, L1 cache, and we don't have to worry about caches at all, both approaches have pretty much the same performance, which is good because despite the added overhead of recursive algorithms, even though we can see that it's not very high, the cache oblivious algorithm implementation does work pretty much the same speed as the naive implementation with none of those overheads. But as the matrix size increases, so x-axis is matrix size, y-axis is the throughput in terms of how much useful work that we actually do, in terms of the work we need to do to actually get the results. As the matrix sizes become larger, the naive implementation's performance has multiple steps of performance degradation as we start thrashing L1, L2, and so on cache. Compared to that, the cache oblivious algorithm still maintains performance. So that's good. That's exactly what we want. And we can we know that regardless of the computer architecture that we run on, in terms of the cache hierarchy size or depth, or the size of caches at each level, this constant performance characteristic will hold because none of those characteristics have been hard-coded into the algorithm at all. So we can always expect this to be high performance. And to give you a sneak peek into what's going to happen in the next couple of slides, next couple of lectures, the lab 1, so lab 1 of 2 of this course will be pretty much based on implementing this with a little bit more flair to it. I'll let you know in a bit. Anyways, as a bonus to doing matrix-matrix stuff with cache oblivious algorithms, another matrix-related algorithm for cache oblivious algorithm for matrix stuff is matrix transpose. We've talked about matrix transpose being good for cache characteristics. And because compared to the n cubed amount of work that you need to do for matrix multiplication, and matrix transpose only requires n squared amount of work because you're only scanning through the whole matrix once, we haven't talked too much about it in detail because the performance overhead of that in relation to everything else is pretty low. But this is also possible to be defined recursively, where A transpose can be expressed in terms of moving these relatively big, small chunks around, where A12 moves here because we're transposing it, and A21, bottom left, moves here, top right, and then we transpose them recursively. And this also is also a cache oblivious, cache optimized method of doing things, just as an aside. So this was matrix multiplication. And the next item in the catalog is trees in search, which is another one of the big basic building blocks of whatever we decide to build. And this is, for me, when I first learned this was actually very illuminating. So binary search trees are actually quite cache ineffective because of the large cache lines. Say we have a binary cache, like a binary search tree like the one you see on the top, right here, and we want to traverse this looking for, say, element 72, and we're going to traverse this tree starting from the root. We go to 50, 73 is larger than 50, so we go to the next one, which happens to be 40, 70, so on and so on. If we look at let's say the tree is implemented in a implicit layout where each layer of the tree is just laid out in memory, it concatenated with everything. So let's say we have the implicit layout of the tree, like the one you see here, where the level one of the tree, the first layer of the tree, consisting of just the root value 50, comes first. Level 2, level 3, level 4, so on and so on. It's laid out in memory in this manner. If you look, superimpose the organization of cache blocks or cache lines on top of this, cache lines would be uniform in size, cache block 1, block 2, block 3, block 4, and such. The issue here is because the distance between the current node that we're visiting in the tree and the next node we'll be visiting by traversing down the tree are far away from each other. We start from node 50, we go right. This one's kind of close because the root node is just one node and the layer 1 is just 2 nodes. But once we go down into bigger and bigger nodes, bigger and bigger layers, every single access that we make as we traverse the tree, next it's 90, next is 70, hits a new cache line. So this becomes pretty much the same situation where we were doing non-transposed naive matrix multiplication, where each element access results in a cache miss. So searching for 72 in this example results in 4 cache line reads. And considering how we only made 4 memory requests and that resulted in 3 cache line reads, that's not very good. And if we had continued further down the tree that's larger, we can pretty much see that every single traversal is going to result in a cache miss. And that would be bad. It depends. I mean, if you care about performance, that would be bad. So, and if this was so far talking about implicit layout of trees, where the location, each node is laid out in a static position, like the one you see on the right here. Often other times you can implement trees by building pointers to nodes that have been allocated in random positions in the block. And you can pretty much imagine that would be even worse if you were to build a tree in the heap. It would be even worse in terms of cache characteristics, because if you're jumping to random locations in memory, every time you traverse down a tree, that would also result in a cache miss per traversal iteration. Right. This means that each traversal iteration pretty much hits a new cache line every single time, meaning every time we traverse down a tree or search a tree, we're going to read log 2 of n cache lines. And that's not good. One better way to lay out this tree to get better cache characteristics is, you would probably have guessed it, recursion, recursive definition of data layout. Trees can be organized also into locally encoded subtrees, meaning the whole tree can be, we'll get into more details in the next slide. The whole tree can be broken up recursively into smaller and smaller trees until a subtree fits inside a cache line. That would give us much better cache characteristics. For example, if we take the tree that we were looking at from the previous slide, depth of 4, height of 4, and then we break up the tree into subtrees of height 2. Here we would have at the root node, we will have a subtree of height 2, 3 elements, because the root is just 1 element. The second layer is 2 elements, level 1 plus level 2. And this this top level subtree will have 4 further subtrees, because we have 2 leaves and each leaf would have 2 subtrees connected to it. We have 4 trees. And each of these 4 trees would have 3 elements in them, because they're of height 2, like everyone else. If we follow this layout approach, then starting from value, the root node, trying to search the value of 72 again, The first access goes into, I mean, of course, if this is compulsory cache miss, it has to result in a cache miss. But the next node that we visit is going to be cached inside. I mean, this is the same as before, so maybe that's not too important. But after we reuse this B1 cache line, then we go to node 90, which results in resulting us needing to load a new cache line for the new subtree. We access node 90. But thankfully, because the node 72, which is the child of node 90, it belongs in the same subtree. And as a result, because the subtree is so small, it also belongs in the same cache line. So compared to the naive example from before, accessing 4 values results in only 2 cache misses instead of 3. And the change will probably become more prominent as the tree becomes larger. Again, as the same as the matrix-matrix multiplication example, if we know the exact characteristics of the cache, we can choose the size of the subtree hard-coded somewhere to make the best use of the cache line size, make the best use of the cache sizes, etc., etc. But the problem is, again, we want to be portable. We want this to be high performance, regardless of any reasonable machine that we're going to run it on. So the question becomes how to choose the size of the subtree. And as before, the answer becomes we choose it recursively, so that at some point in the recursion we happen to pass by the correct value. So there's a recursive tree layout approach called the Van M. de Boas tree layout. And this is going to get a little bit involved. And like most things I'm going to talk about in this lecture, this is pretty much just to see if the plan have this idea in the back of your heads, not necessary to memorize the time complexity analysis and things like that. So maybe we can kind of move into this in a relaxed fashion. So the Van M. de Boas tree layout organizes the tree into, recursively organizes a binary tree. Some caveats is that it needs to be balanced to be efficient, and we'll get into why in a little bit. And we do recurse down until the subtree size is either 1 or some size that we know for sure will fit inside the cache line. So we start from a tree of size h, height h that we see here, and the implicit memory layout you see on the bottom. We're first going to chop the tree into halves so that the height of the upper tree becomes h divided by 2, height of the lower trees becomes h divided by 2. And this will be encoded in memory as such. Top tree A goes here, lower tree B1 to BKs go to the right. The number of k would be, because the height of A is h divided by 2, the number of k would be 2 to the power of h divided by 2 times 2. Many trees of B's. And we further divide the tree into halves, h divided by 4, and also for all the other trees. And we continue this until we get to a subtree size, which absolutely fits in a cache line. In terms of cache access, when we recurse down the tree search, for example, we recurse down until the leaf has a number of bytes the same or smaller than cache line, green, because the green subtrees here are meant to represent the leaves. And the subtree height becomes log 2 of B, where B is the cache line size. So we're going to traverse log B to the n leaf trees. So we're going to have to make the log B to the n number of cache misses. But like I mentioned just a few seconds ago, these numbers themselves are not very important. What's important is that we have come up with the, I mean, not me, but there is a recursive layout of trees in which as we traverse down the tree, hopefully we're going, we're going to pass by multiple levels of the tree sizes, subtree sizes, in which these trees are going to either fit in the cache line, or the trees are going to fit in cache line sizes pretty much, without us having to actually know the size of the cache lines. So if you look at the performance of the Venom-DeBoas tree layout, this is kind of a complicated chart. Let me get into the details just a little bit. X-axis is the size of the tree in terms of height. Y-axis is the exponential scale, the logarithmic scale in terms of time. So lower is better, exponentially. The Venom-DeBoas tree layout is the one marked with a plus. So the one next to my eyes here. The naive implementation, the breadth first search implementation, is the X's here. And the not the breadth first search, the binary tree. The binary tree implementations, a special binary tree implementations where the each node size is either 8 or 16 nodes, so not binary trees, but more like B trees, are down below, either 8 or 16 children per node. And the performance you see is the Venom-DeBoas trees implementation is faster than the naive implementations. But interestingly, it's not faster than if you had built a B tree, which has a children size optimized to the size of the cache line. So if you have 16 nodes per node, 16 children per node, that's something like 16 multiplied by 4 byte pointers or 4 byte indices is 64 bytes, which is the cache line. So if you have cache line optimized B trees, so that every time we load a node, we make use of pretty much all of it for various reasons. The added overhead of having this recursive complex layout actually does worse. But compared to just regular binary tree implementation, as the sizes of trees become larger compared to the naive binary tree implementation, the performance actually does make up for, the cache performance actually does make up for the added complexity of the algorithm. So if I just showed you this chart, the answer might be, why bother with this complex cache oblivious algorithms for trees if we know pretty much not to, I mean, it won't be too big of a stretch to think that our cache line is going to be 64 bytes or maybe slightly larger. So maybe the best idea would be to simply use a B tree with a high number of node sizes, either 8 or 16 nodes per children nodes per node. And that's absolutely a valid solution to make. Indeed, if you were dealing mostly with, say, in-memory algorithms with on Intel x86 machines, I think that would pretty much be the correct way to go. I guess the only change from before having seen this deck of slides from now would be that you would, the choice of the B tree would be also driven by the cache characteristics of the B tree as opposed to the binary search tree. The cache oblivious nature of this algorithm shines a little bit more once we get to further down the memory hierarchy. So this is an example of the performance of the same binary search tree compared to the Venom-DeBoas tree, compared to the B tree. But this time we're also looking at a large enough tree that it's going to spill over from memory into things like swap, into storage. So when we look at the performance of the tree size when it's small enough to fit in memory, and here we're not doing anything special with the storage accesses. We're just going to let swap space handle storage access. We're just going to malloc a large enough memory size to store this entire tree, and the operating system will just try to do its best to use the swap space to move the because the tree is going to be larger than the size of the available memory, the operating system will try to do its best into moving some of that into storage and moving it back when it's accessed. So when the tree size is small enough to fit in memory, and I don't know if it's very visible, but yeah, the Venom-DeVos tree is slower than the binary search tree. But as soon as we move to a size that it starts hitting the storage, this chart would be more impressive if we actually had the 6 and 8 node bullets from before, but maybe I should create one. Anyways, once we start hitting the storage, the performance of the Venom-DeVos tree still does as good as the best of the other implementation, which is the B tree with 1024 children nodes per node, as opposed to the small number 8 or 16 from the previous slide. And 1024, having 1024 subtrees, subnodes is chosen because in order to not to make the use of the whole, I mean, I guess it is to make the use of the whole cache line. It is to make the use of the whole storage page that you have to read, because the storage page in Linux at least is 4 kilobytes. We want to fit, we want to make use of the whole page when it's read. So compared to using these hand-optimized magic numbers for these B trees, and I mean, still using these B trees, these hand-optimized numbers for B trees is an absolutely valid thing to do, especially if you know the size of the problems that you're going to deal with, and especially if you want to deal with storage accesses explicitly, which is often a smarter thing to do. But if you want to have an algorithmic solution that adapts to whether if the data is coming from storage, or whether the data is coming from off-chip memory, or whether the data is coming from cache, automatically without having to know of the things like cache line sizes or having to know the size of the storage pages. And this is an absolutely algorithmic, elegant approach to solving this problem. Yes, because the question is, how do we optimize for n in high n? If we know that we're going to access storage, we need to choose a very high n, for example, 1024, to match the granularity of storage page accesses. Databases often use n's optimized for storage pages because kind of optimizing for hiding the storage access latency is one of their biggest goals. But yeah, if you want to handle optimally both storage access and off-chip DRAM accesses, then choosing the magic value for n becomes a slightly complicated problem. May not, depending on how you approach it, but this is another potential way of approaching this problem. Oh yeah, I mentioned this already. And kind of as an aside of talking about the Venom-DeVos trees, the Venom-DeVos trees is actually a tricky data structure to do correctly, because when you do, because they only work very well when the trees are balanced. And to maintain the balanced nature, it's actually a kind of tricky data structure to do inserts and deletions, and then rebalance the recursively defined data structure. But it is a good thing to have in the back of your head, I think. For a simple approach, a simple scenario in which this may be useful would be if you construct a tree in the beginning and you have to read it multiple times, for example. All right. So next in the catalog, we have 2 more left. Hopefully we have time. Is merge sort, which is a problem I'm quite fond of. At the beginning of the lecture, I mentioned try implementing quicksort or whatever and try to compare the performance against std sort, and you will see a big difference. And here we talk a little bit about why that is. So here's an example of the animation of the sorting algorithm that I found online. Let's see if I can actually start it. We can implement merge sort. I'm sure you're all familiar with merge sort already. You can implement merge sort in Hey, why did it stop? You can implement merge sort in, well, I'm sure you can implement it in multiple ways, but you can implement it in two different ways as well. You can implement merge sort in a depth first fashion or a breadth first fashion, where you sort the data in all the small chunks are sorted first, and then you recurse up in terms of layers. Or you can pretty much you can either decide to recurse the sorting tree, merge sort tree, in a depth first fashion or a breadth first fashion. For example, if you look at this animation, you can either sort all of the little chunks first. You can sweep the whole data set, sorting the little chunks first. Or you can start merging the sorted chunks as soon as possible to turn them into larger chunks before we move on to the next chunks. So this is two different approaches, at least when we're talking about merge sort. If you compare these two approaches, the depth first search, depth first merge sort, where we merge the sorted chunks as soon as possible. As soon as there are consecutive chunks that are already sorted, we merge them as soon as possible instead of waiting until the whole data set is swept. The former method is better in terms of cache efficiency because we only need to do log n full accesses on data, full sweeps of data for blocks larger than m, where m is the size of the cache. As opposed to the breadth first method, where we have to do log n full accesses on data, full sweeps of data, period. Because we're not getting any cache effects, because every time we come back to the beginning of the data set, the beginning of the data set would have been the data that we just sorted have been evicted from memory already, evicted from cache already. But even compared to, if we can go even further, a binary merge sort, but not a binary merge sort. Instead of merging two blocks at every sweep, if we merge more blocks at every sweep, say R, it would be more cache efficient. Because instead of doing log 2 of n full accesses of data, we'd be doing log R of n full accesses of data. And that becomes, the amount of work doesn't change. So in terms of time complexity of the algorithm, it stays exactly the same. But if we think about memory accesses, the total number of cache lines that we have to read, the total amount of data that we have to read to cache from the off-chip memory becomes exponentially lower as the number R increases. The way we can use this, and we'll get into detail of this in a little bit, is by using a tournament of mergers, like such. Instead of having two partially sorted blocks being merged into one at every sweep, we can have R number of partially sorted blocks. For example, if here R seems to be 4, and at every sweep, we can compare 4 values for when R is 4. We can compare 4 values from each partially sorted chunks to decide on the next value that we're going to put in the sorted chunk. This is a pretty straightforward enough way to implement this. And just by choosing a larger R, you'll pretty much see performance increase immediately. The difference is pretty much night and day when you implement merge sort. Again, as usual, the cache obliviousness problem comes in where we have to actually choose the value of R. If we choose an R that is too greedy, if the R size is too large, then the tournament merger spills out of cache, resulting in the single sweep merger thrashing the memory, giving us a sharp performance loss. Again, if we choose a small enough R, then we leave performance on the table, which we want to avoid. Of course, you can choose a pretty conservative number for R, say 8 or something, and there is a saturation point in terms of performance as R becomes larger. So that's probably not the worst thing to do in terms of performance. But just for the sake of elegance, we can try to figure out the algorithmically most efficient way. So to do an analysis of this, we can first talk about the topic of a lazy K-merger. What a lazy K-merger is, it's a recursive definition of merger, as usual. So instead of having just a tree, a hand-coded tree of mergers, taking input from R pre-sorted chunks and emitting into one, we can have we can define a merger which takes K number of inputs and chop that up into recursively chop it up into smaller and smaller mergers. Always by chopping it into half, just like we did with the tree before. The caveats, not the caveats, the details, some of the details of the lazy K merger that we, I guess, need to remember to get the maximum performance out of it, is that each submerger, the little trees that we see here, has a K cubed element output buffer, depending on the size of the input. For example, if this whole triangle, this whole merger has 4 inputs, decides to take in 4 inputs, we need to assign at least 4 to the power of 3, which is 64 element output Q for this algorithm to run in an optimal way. Of course, as we could recurse down, this second level recursion has square root of K plus 1 submergers. And square root of, because there's square root of K mergers on this level and 1 here, so square root of K plus 1. So these square root of K submergers feed into one submerger. Each submerger has square root of K inputs, because K is being square rooted, K here, we're chopping things up into half. And because each of these submergers have square root of K elements going in, each of these lower mergers need a K to the power of 3/2 element buffers, because we need K cubed element output buffer for input number of K, because the input number here is K square root of K, the output element needs to be K to the power of 3/2. And we can recurse down until the fan-in is very, very small. And I think I have another, yep. We can recurse down until the K is very, very small. And algorithmically, and this does look a little bit involved, but I assure you the algorithm itself is very, very simple. The top level merger, the smallest, the biggest, the top level mergers exposes a procedure, a method called fill. And when the fill is called, while the output buffer is not full, so we loop this until this whole thing is full, if the left input buffer is empty, we call the fill of the left child. So we want this to be completely full before we do anything. And then if the right buffer is empty, we call fill again. So we want to fill this completely. So we want, naturally, we don't want any of these queues to be empty. So if we discover anything is empty, we do work until these queues are completely filled. And then once these two are either completely filled or not empty, we do the R-way merge and we fill out the output until this is completely full. So in terms of memory usage, each K merger, because we chose numbers like K cubed, each K merger fits in K square space, which gives us ideal cache effects. And again, like most things we talked about, the proof for why gives us ideal cache effects is we're not going to go into details. And the question here is, what should the K be? It is a single number of K, which is not actually tied down to the cache hierarchy numbers. but tied down to the, I mean, you have some freedom of choosing K. It's not going to impact the performance based on cache effects. This is more of an algorithmic thing. But given n elements, choosing a K value of n to the power of 1/3 is a special way of doing sort called the funnel sort. Funnel sort is the cache oblivious sorting algorithm, which all of this leads up into. And oh, and I guess we can, yeah. And here I'm going to take the chance to say that implementing, like I mentioned a couple of times already, implementing pure funnel sort is, I don't know if it's the correct way to do any of this at any given, in most cases. Personally, because there are saturation of performance as we get to complex and complex solutions, personally, I felt that building a lazy K-merger based sorting algorithm based on a reasonable number of K did work pretty well for me most of the times. We don't have to try to, I guess, get to the bottom of everything. Because unless getting to the bottom of everything is your goal and you work on algorithms, then absolutely you should. But when we're building systems, there are oftentimes a good trade-off between performance and complexity. Right. So if you look at the performance of funnel sort, the cache oblivious sort algorithm compared to everything else, if you compare against the sorting algorithm used in, I think this is GCC. Again, as usual, the x-axis is the size of the data set. Y-axis is the logarithmic time, wall clock time. So lower is better. So compared to the STD sort, which actually uses, I think, I'm having trouble coming up with the name. It uses a hybrid sorting algorithm based on a couple of sorting algorithms, including insertion sort and quick sort and whatnot. When we look at very, very small sizes of data sets, so log of n, so x-axis is log of n. So if you look at data sizes of a few thousand elements, when cache effects aren't that important, compare that to funnel sort, these lines here. The overhead of the complexity of the algorithm does result in faster performance by the GCC. But as we get to larger and larger data sets and performance becomes more impacted by cache effects, then we do see a lot of performance improvements with larger data sets. If you look at the same experiment running on a different system, these are still very old systems, so the numbers and relationships may have changed recently. But I think if they have changed, they would have changed in the direction of the former chart than this one. In this machine, the Pentium 4 machine, the off-chip memory access performance in relation to the CPU computation performance was kind of higher in this one. So that even with worse cache effects by the GCC algorithm, they still maintain their relative performance advantage because the performance here is not bottlenecked by the memory accesses, it's being bottlenecked by the throughput of the processor. So I guess there are two takeaways from this. One could be that you do need to know kind of the system that you're building on, because you might end up writing a complex cache oblivious algorithm and run into a situation such as this one. But I'm pretty sure with modern systems with better, faster processor performance and memory performance not increasing as quickly. On top of that, if you deal with multi-threaded stuff, as we're going to talk about in the next in the couple of slides down, we will absolutely see a performance crossover with larger data sets. Speaking of larger data sets, if we go to storage again, similarly to before, we're not handling storage in any special way. We're letting the operating system handle it. The impact of not handling cache effects becomes much worse with larger access granularity of storage and the higher latency of storage. And having a good caching characteristics by funnel sort here becomes more important as the data set becomes larger. Of course, if you use a storage optimized library, the storage becomes different. But it is an oblivious, cache oblivious way. It is a storage or memory system oblivious way to consistently get high performance. All right, that was sort. The last one in the category catalog is stencils. I think we can, I'll try to power through all of this. For those of you who are not familiar with stencils, stencils computation is a way of solving partial differential equations in a iterative simulation kind of an approach. So an example here is if you look at a heat diffusion example, uses a partial differential equations to simulate heat diffusion as time goes on. This equation itself is absolutely not important. All it says is the temperature of this of a cell of a location is dependent on the temperature of the surrounding cells, X, Y, and Z, described using a bunch of partial differential equation. And if we had time, I would go into this, but we don't, so we're not going to go into this. The bottom line is that this complicated algorithm, complicated numerical thing can be expressed in terms of iterative computation, where a cell, we divide the system into cells, where the cell of the value of a cell at the next time step, this is where the delta t comes from, depends on the value of the current cell plus the value of the surrounding cells. We're looking at a one-dimensional example of this right now, so only plus x and minus x. So we're described graphically. So x-axis here is x. We're looking at a one-dimensional example, and we're looking at how the values change. I guess in the heat dissipation example, how the values change as time goes on. So as along the x-axis, we're seeing the time move. Yes, the bottom line is that the set of the temperature, let's say, of the current cell at the next time step can be calculated using the current time step, the cell to the right, cell to the left. And this computation expressed in this way is a stencil. And the stencil updates each position in the cell using surrounding values as input. And here, this example is a one-dimensional 3-point stencil because it looks at the left value, the current value, and the right value to calculate the values for this cell in the next time step. There are many important and interesting stencils used to solve different scientific partial differential equations, including things like 2-dimensional 5-point, 2-dimensional 9-point, 3-dimensional 7-point, 3-dimensional 25-point stencils, et cetera, and these are popular for doing things like simulations, fluid dynamics, solving linear equations, and partial differential equations. And some important stencils like a 19-point 3D stencil for doing fluid dynamics, and 25-point 3D stencils for wave propagations. And the thing about writing stencils in a naive way in software, again, using the one-dimensional 3-point stencil as example, if the dimensions of the grid that we're looking at in a one-dimensional stencils, if the length of x, unless the length of x is small enough, there is no cache reuse, because if you simply scan over the entirety of the x at every time step, by the time you come back to the beginning of x for the next time step, the data for that would have been evicted out of the cache already, like such. The yellow block here is the size of the cache. So continuing the theme, can we recursively process this data in a cache optimal way? And yes, we can. course. And one approach of doing cache oblivious stencil operations is dividing the work into trapezoidal units. The computation in a trapezoid is either a self-contained shape that does not require anything from the outside, the trapezoidal shape you see here, the red one here, because all of the cells in this trapezoidal shape, because they only read data from either the left point in the previous time step or the right point in the previous time step. So as long as we have all the values for the black circles at the bottom here, we can calculate all the values for this trapezoid without requiring any data from the outside world. It's completely self-sufficient. Or other shapes that use data that has been computed already, such as this triangle here. This is not self-sufficient, but if this trapezoid, the red trapezoid, has been handled already, then this thing can be completely calculated, but only after this red trapezoid has been completely calculated. So you want to recursively chop up this problem space into these trapezoids so that at some point we will hit cache efficiency. So one approach to doing this is the following. We can recurse down the total size of the problem by doing cuts. One cut we can do is a space cut. If the width of the trapezoid, the red trapezoid here, you see here, if the width is larger than or equal to the height multiplied by 2, we can cut the trapezoid through the center, the red line you see here, using a line of slope -1. If we do this, we can process the left trapezoid and then process the right trapezoid, because the right one depends on the left one. The second type of cut we can do is the time cut. If the width is smaller than height multiplied by 2, like the right trapezoid you see on the right here, we can cut the trapezoid with the horizontal line, the red line you see here, through the center. We can process the bottom and then the top. And we can continue down this recursion path until the trapezoids themselves become small enough that each of them fits entirely in cache, so that when we are when we are doing the trapezoidal computation, we can do it completely within the cache without having to make any off-chip memory accesses. And this works pretty well. Intuitively, trapezoids are split until they are of size n, cache size. And the total data reads that we have to do would be n multiplied by time divided by m. And this is a pretty good cache effect to have. This is pretty much optimal way to do cache effects. And that's good. Compared to just doing linear computation, the performance difference is again night and day. Before we get into any of these details here, if we compare it to doing serial looping, the naive implementation, I think the size here is 2000 by 2000 again. Serial looping takes 128 seconds as opposed to serial trapezoid. So single thread trapezoid, the performance improvement is almost 2x. But the thing is, the vanilla method of doing these cuts are not very good for parallelism. For example, if you look at the 3 splits that we made here, 1, 2, 3, they have very strict dependencies of operation. We have to do process this triangle first, and then this trapezoid, and then this trapezoid, regardless of the kind of, regardless how many processors we have, how many cores we have, this becomes a pretty serial operation because there's not much parallelism we can exploit from it. A different way of doing space cuts would be to make it parallelism friendly. Instead of cutting this thing into 2 parts, we can cut it into 3 parts, where these 2 trapezoids can be processed in parallel, and then this trapezoid can be processed. There's still dependency relations, because this inverted triangle can only be processed after these 2 have been done. But it does exploit a little bit of parallelism. And the interesting thing here is that if you look at the looping method, which is naive, non-cache optimized way, and we implement it in 4 threads, the performance improvement of the looping method is only almost 2x, which is not bad. Because depending on how you loop it, this can be a completely naive, embarrassingly parallel problem. We can chop up the problem into vertical chunks, and they'll be completely embarrassingly parallel problems. Not completely, but almost embarrassingly parallel problems. We're not hitting 4x performance with 4 threads. As opposed to the trapezoidal method, parallel aware trapezoidal methods, where when we have 4 threads, we actually get 4 times the performance, as you see on the right here, almost 4 times, 3 times 9, 6. Yeah, when we have better cache effects, it actually does have an impact on parallel scalability. We'll get into details on why this is in one of the later lectures, but at this point, what's happening is that we are hitting the DRAM bandwidth bottleneck because the looping method has such a bad cache effect that a lot of the memory accesses are being made off chip. And when multiple threads compete for memory and they're all making a lot of memory requests, we can very quickly run out of DRAM bandwidth. And that's what's happening. We've hit the memory bottleneck for off-chip DRAM, as opposed to the cache effective method, which has not. So in overall, even though in a single thread implementation, this comes up fairly often, this relations and this will come up absolutely in lab 1 as well. Compared to the single thread performance relations between the non-cache optimized and the cache optimized method, if you look at the multi-thread performance relationships of the non-cache optimized and the cache optimized method, the difference is much, much more significant. All right, that's the, we overshot time a little bit, but hopefully not too much. So that has been the high-level introduction to cache oblivious methods of making better use of cache hierarchies. And the next lecture, we're going to show that all of this approach, how we have finally moved the performance bottleneck away from the cache. If you remember, beginning at the very first lecture when we were talking about cache matrix multiplication, ever since beginning from the naive implementation of the matrix multiplication, all of the improvements, subsequent improvements we made so far has brought about performance improvements because we were using the cache in a better way. But in the next lecture, I'm going to show that we have reached kind of the limit of that. So the memory is being used in as efficient way as possible. And now we can do better by improving how the processor does computation better. So hopefully jumping to that new topic is going to be even more interesting than what we've seen so far. Cool, thank you. If you have any questions or anything, I can stick around. Please let me know.